Hello and welcome to this presentation for the ICPE 2020 conference on the efficacy of a blended learning mastery progression cycle on achievement and attitude in high school science. My name is Sam Roberson and I'll be presenting the findings of this research, which was the product of a doctoral program under the supervision of Martin Cooper and Robert Kavanagh at Curtin University. This presentation will outline the context of the study, the research questions addressed, a summary of the literature around the relevant conceptual frameworks, a brief overview of the methodology, the project findings, and some implications for teachers. The purpose of the study. With the proliferation of ICT student-provided devices and lockdowns associated with the COVID pandemics, there has been an increasing trend towards blended learning and the flipped classroom, with content often delivered asynchronously. There is a substantial body of research which demonstrates the benefits of mastery approach to learning, and more recently software developers have begun producing mastery-based learning programs. However, there is little empirical evidence regarding the student performance outcomes in this context. So the purpose of this study was to investigate the efficacy of combining both blended and mastery learning approaches in a blended learning mastery progression cycle through the use of a commercially available web-based program to measure mastery to deliver the corrective activities. The research question addressed overarchingly was whether a combination of these approaches, specifically through the use of the Minds on Physics program, would affect student academic performance and attitudes towards science. The term mastery learning is frequently used to describe approaches that emphasize the sequential learning with regular checks and feedbacks to students, combined with corrective activities that address the identified gaps in learning. A key aspect of mastery learning is that students are required to show mastery of the concept before moving on to the next stage in the curriculum. Mastery learning approaches are frequently modelled on Bloom's learning for mastery cycle, in which students perform individually mastery assessments which identify areas of misunderstanding in the concept or topic. They are then directed towards corrective activities which are specifically aimed at the identified misconceptions. Students then attempt a reassessment of their mastery and work their way around this cycle if more corrective activities are required until they demonstrate mastery of the required concepts. It is a directed application of specific corrective activities that characterizes effective mastery progression programs. These correctives are learning activities that present the same content as originally taught in perhaps a group phase of instruction, but in a different format. This allows students to develop their understanding using a variety of different cognitive processes. In this study, the corrective activities were based on blended learning approaches. The term blended learning is often used to describe any method of teaching with technology. However, it may be more appropriate to define it in terms of the learning. A more learning-centered definition is built on a combination of different concepts, but based upon the use of web-based technologies to accomplish an educational goal, the combining of educational pedagogical approaches, and the combining of instructional technology with some face-to-face instructor-led training. Due to the increased availability of cost-effective IT solutions and more recently the increase in remote synchronous and asynchronous learning due to COVID lockdowns, there has been a heightened interest in the use of blending and learning approaches. Common blended learning approaches may include the use of multimedia learning activities, simulations, videos, and such. As this study aims to assess the efficacy of a new approach, the measurement of the impact of this approach is a key aspect of the research. For this research, the efficacy was taken to be measured in terms of both attainment and attitudes. In this context, the term attainment was taken to mean the ability of students to respond to questions and problems through the application of concepts that they had studied in the topics, and this was assessed in a pre- and post-unit use of the force concept inventory. This is a commonly used measure of student understanding of Newtonian concepts. Students' attitudes towards how subject can have a significant impact on their application to study and hence their achievement. For this study, the scales of the TOS rule were used to measure students' attitudes towards a number of science domains. Here's some examples of the force concept inventory questions as a multiple choice assessment where the distractor responses are based on the common misconceptions that students may have around the topic. Here is an example of Section 1 of the TOS rule, which investigates students' attitudes towards scientific inquiry, which you might consider to be their attitudes towards experimental learning. As can be seen from the diagram, the study adopted a quasi-experimental design methodology through the use of an intervention and control approach. The construct model for this study relies on the premise that students have misconceptions in their understanding of Year 10 physical science curriculum, and it takes a positive view that this different learning activities can lead to different outcomes in terms of the attainment and attitude towards a subject area. The implementation model is shown here. As can be seen, all students completed the same initial learning activities, but the intervention groups then completed mastery and corrective activities at regular intervals throughout the unit. Pre and post unit, all students completed the force concept inventory and TOSRA scaled surveys. The Minds on Physics platform was used to assess student mastery of the concepts and to provide access to corrective activities. Here is an example of the questions used in the mastery approach, and if students are continually incorrect on a particular concept, they have a message which directs them towards a corrective activity. Corrective activities are blended learning in that they are web-based. And there are some examples here. Some of them are simple text information boxes, directions to perform a lab either physically or an online version, and interactive simulations such as the one shown here. The sample consisted of mixed gender classes from a Year 10 cohort from the Queensland High School, Year 10 core science classes, which means they're across the range of abilities. Control group size, treatment group size are shown with a total sample size of nearly 200 students. The particular school was chosen due to its excellent ICT infrastructure, including a one-to-one laptop scheme across the school, and hence a high level of digital literacy amongst students. Here is an overview of the force content inventory results for both treatment and control groups, and presented graphically. We can see that the pre-unit means are similar, but post-unit there is a larger variation in the means. Both treatment and control groups improved the mean force complementary scores, but the change is higher for the treatment group. If we consider this data in light of the research questions, it was found that there was a significant difference. There was not a significant difference between the pre-unit scores for the treatment and control groups, which indicates that the two groups could be considered to have a similar understanding of the force concept inventory. For both the control and treatment group, it was found that there was a significant difference between the pre and post FCI scores, with an effect size of 0.81 for the control group and 1.47 for the treatment group. When comparing post-test FCI scores between the treatment and control group, we've seen already that there was a difference, but this difference was statistically significant. The control group mean difference of 2.3 being statistically significant, with the effect size difference of 0.66. In terms of the attitude results, they are presented here by looking at the box plots provided for each of these. We can see that there appears to be little difference between the control and treatment groups in the pre and post test results. This is reflected in the statistical analysis, which showed that although there was a small statistically significant difference between the pre and post unit TOSRA scores for all scales for both control and treatment group, there was no significant difference between the groups at either stage. In conclusion, we've shown that the blended learning mastery progression cycle led to improvements in understanding of the force concept, the Newtonian force concept, as measured by the force concept inventory. It appears that the intervention had no significant effect on students' attitudes towards science, with both control and treatment groups having small improvements across all domains, but no difference between the two groups. It appears that blended learning activities are effective as correctives in improving student understanding using a mastery progression cycle. Implications for practice for teachers and educators. Our research provides further evidence for the support more generally of mastery approaches, in particular the use of blended learning or online activities integrated into mastery approaches in the corrective phase. We've also shown that some commercially available resources appear to actually do what they're supposed to do.